Good evening, everyone. Welcome to our monthly seminar series here at the Fields Institute in Quantitative Finance. Before introducing the speaker, I'd like to thank our sponsors, Scotiabank, through the Center for Financial Industries, for their continual support, as well as Waterfront International for their support specifically of this seminar series through the years. So thank you very much. Next, I'll introduce our speaker today. It's a pleasure to have Dr. Cristian Bravo. He is a professor and a Canada Research Chair in Banking and Insurance Analytics at Western University. He also serves as the director of the Banking Analytics Lab, and his research lies at the intersection of data science, analytics, and credit risk, researching how techniques such as multimodal deep learning, which we'll learn about today as well in certain contexts, causal inference and social networks can be used to understand relationships between consumers and financial institutions. He serves on the editorial board of Applied Soft Computing in the Journal of Business Analytics, and he's also the co-author of a very popular book called Profit-Driven Business Analytics, and I urge you to check it out. Unfortunately, I don't have a copy in my hand to show it to you, but please check it out on Amazon.
Or wait a year for my new one, Deep Learning in Banking, coming widely 2025.
Sounds like an infomercial.
That was the joke, mate. Yeah.
With that, please join me in welcoming Dr. Bravo.
Thank you, Seb, and thank you everyone for both coming here on Wednesday night and to hear me rambling about stuff. I see that the camera is fixed, so I'm gonna try to stick around here. I apologize. No, it doesn't. Look.
It's not following? No, when you go out of frame.
Yep.
Stay there. Move around a bit. Yeah. Okay. Yeah.
Nope.
Okay.
Yep. Okay, so I'm gonna stay on frame here. That's gonna be a lot more boring, but okay, I'll try my best. The topic of my talk today is, and again, thank you everyone, and thank you, Seth, so much for inviting me. It's always a pleasure to be here at Fields. And so my topic of my talk today is financial risk contagion models using dynamic multimodal graph learning. I'm going to split this out as I develop the talk, right? So this word salad doesn't sound so saladly. This is a collaboration with Christoph Muse from the University of Southampton and Maria Oscarsdottir from Reykjavik University for the next couple of months, now moving to Southampton. So you see it's actually how the market moves. So I'm gonna start introducing my group and myself a little bit, right? And speaking about financial contagion, and I have two cases for you today. So how long do I have, Seth? 45 minutes plus 15 questions? Okay, perfect. So I have 47 minutes. I'm going to tell you about two cases, one in corporate credit risk and one in small business credit risk, both of them done with different institutions. If you were here at COMBAF a few months ago in July, right here, so I know you were, you probably heard me speak about one of these cases. The other one will be completely new. And then I'm going to conclude and speak a little bit about some conclusions on future work. So with no further ado, let's continue. So a little bit about us. As I said, I lead something that I call the Banking Analytics Lab. You can scan there and see our website. We're one of the largest groups in the world in studying retail credit risk and data-driven credit risk. 3 postdoctoral researchers for a while to our living now. No, 2, sorry. One is now a professor in Laval. The other 2 are leaving soon, so no postdocs in a little bit, but around 12 PhD students spread out across 12 continents between the UK, Iceland, and here. A large network of collaborators all over the world. Yay! Now it's follow me, I can move. Thanks. I do enjoy that. So, and I think that we've gotten sufficient recognition, and I'm not gonna read that. This is our website, but one of the things that I think that we do really good, well, is we collaborate with a whole bunch of companies worldwide, right? So here you can see some of them. 2 of them are the ones that are going to be related to the project. I mean, you know how these collaborations are. I cannot really tell you which company specifically the project is with, right? But it's super obvious when you see the list of co-authors. So yeah. So that's us. Let's speak a little bit about one of our core research topics, which is financial contagion, right? So, I mean, this is a seminar in finance. I have this slide just in case. What is credit risk? if you're sitting here, you probably know, but just for the sake of discussion, credit risk is the risk of a counterparty of someone that you gave money to, or you gave something, well, money, not paying it back, right? In the most simple ways, of course. But from the point of view of, if you want the regulatory thing, that's not here. The credit risk is reflected as, or is defined as, the risk of a counterparty in a financial transaction to not satisfy or be believed not to satisfy their financial obligations towards you. So a bank can declare someone in technical default when they haven't defaulted yet because, I don't know, you saw the company burn down in flames, right? Or sometimes it has happened that you see that the company is going bust, they appear in the new going bust, but they haven't declared or they stop paying, you can declare them right away in default. So that's what this is. And we normally use credit scoring for this in retail lending. So when you probably have a credit score, you probably know what a credit score is, you have been in some way related to it. And I like to say it's probably one of the oldest applications of data science and analytics, right? Because we have been using data-driven methods to identify whether someone is going to pay back obligations towards you or not for a long, long, long time, from the 60s. So in fact, the very first application comes from Durant in 1941. So when data science was something that was almost a century far, right? Yep. So now we use it for everything, from insurance to give you loans, to renting, to jobs, to whatever. There is a whole ethics discussion on whether we should, but that's not the topic of this talk, right? But we do know that now it's used, for example, in Ontario, it is explicitly allowed to use credit scores for insurance. And that is explicitly forbidden in 5 out of 50 states in our neighbors down south, right? So we can see that these things permeate through society across a whole bunch of things. And let alone, I mean, this is super important. For countries, their credit score is called the country credit rating. And you see how important it is. Every time that there is a change, it's national news. For corporations, it actually depends on whether they are investment grade or not. So really, credit scores or credit ratings are one of the most important statistical measures that we have in the economy today, right? And studying it, it's fun, and I think it's relevant, right? But of course, hopefully I can convince you of it in this presentation. So now let's think about risk. You do not live in a vacuum. No matter who you are, you may be Apple, you may be Canada, you may be you, but you don't live in a vacuum. Your risk is shared and somehow codependent of other people. So for example, one thing that we did, I started my career, right, in studying agricultural lending, right? So lends to farmers. And we realized very quickly that it was correlated because if you get a pest, so you plant avocados and you get a pest, your neighbor is a lot more at risk of getting the same pest. Why? Because the plants are literally one next to the other, right? So there is a risk that is shared just by existing. So like, okay, but that doesn't apply to retail lending. Of course it does. You may work at the same company. If your company is in a downturn, your risk of being let go is a lot higher. If you live in the same neighborhood, probably the economic fields that are dependent of prosperity in your neighborhoods are going to be similar. Maybe you live in a whole city that the city is dependent on 1 or 2 employers for smaller cities. So you see, risk is always shared, has always been shared, no matter the level, for people, for companies, for countries. Okay? So for example, in 1999, the Black Goo Plague in California affected a large number of vineyards, right? So the wine price was affected that year. And then in 2015, a drought in California costing 1.8 billion cost losses because of the drought. You see, they are all the vineyards on the same terrain, and then we're all subject to the same climate risk. Of course, in agricultural lending it's obvious, but hopefully I was able to argue a few examples of when it's not directly obvious. And we're going to see how we can properly measure that, right? Sometimes those two things happen at the same time. That's the multi-layer now. So you can see one layer, what you're doing, a second layer where you are physically. When you put the two of them at the same time, you get a multi-layer problem. And that was a risk that happened in India, for example, where there were floods and droughts at the same time, which is an irony in and of itself. How can that happen? Well, it rained somewhere else, increased the water of the river, but the place itself was dry. So they had simultaneously floods and droughts, right? Which is insane when you think about it, right? And that cost specifically affected rice plantations in 2015, right? And there is one more property of risk. It's dynamic. As we said, for example, if there is a large employer and that employer is doing poorly, then we're going to see that the whole place is having shared risk effects. At the same time, if the risk is, if the company is doing well 10 years later, then we see that it increases. So it moves, it depends, it varies depending on the macroeconomy, the microeconomy, your decisions, the decisions of everyone, right? You can break correlations to companies that were highly correlated as one grows higher than the other one, right? The one that has grown a lot maybe now shakes the relationship that they had with the other one because now they can withstand more on their own, right? So risk is correlated, risk is dynamic, right? And shared among participants. That's the correlation point. So a whole bunch of things evolve over time. Think about fraud, right? Fraud evolves. Fraudsters get more, get smarter. So now we've seen cases of phishing that use AI-generated voices of people. I have told my mom, for example, since there are many recordings of me speaking, probably this talk going to be one of them, to never believe a call from me asking for something unless you can verify it. Because a highly sophisticated fraudster can actually clone my voice and call them with my voice, right? Probably no one will do it because I don't matter in the grand scheme of things, but it's possible. Why not, right? Okay. When we think about it from a network theory point of view, what we see is that if two people are connected, right, nodes, so the people itself can disappear, right, dead or participating, people moving places, right, or edges can appear and disappear. We were connected for some reason, we were doing business transactions together, and now we don't, right, or vice versa. So what we see is that this vision of risk that is ingrained in regulation, by the way. If you read the fundamentals of the Basel regulation, it's going to say this applies to very large portfolios in which every individual is tiny in comparison to the portfolio. Okay, that may be the case, but also absolutely independent of each other and just correlated by a magic correlation factor rho to the economy, right? And the whole banking regulation is based upon that principle, on those models that Michael Gordy designed in the 90s. In fact, there was a very interesting presentation a while ago about whether the rows that were measured by regressions in the 90s still applied in 2024. And the answer is, if you are the US in a very specific condition, yes. For everyone else, no. So yeah. So risk is shared. Risk is dynamic. So what? Risk is propagated. That's the consequence. If you consider people absolutely independent, you are missing a very important determinant of risk. How you, your company, your country relates to the overall economy. What I'm going to show you today is that even though economists and people studying network science have done this at a macroeconomic level for a long time, it requires some highly sophisticated techniques, such as the one that we're going to see today, to do it effectively at a level that we're happy with, at an individual level, either an individual business, an individual company, or an individual period. Okay? So I'm going to be using some way. This is a relatively simple way given the state of the art of mixing it. So I'm going to mix and match a few models, gonna make them talk together, and I'm gonna create one model that is coherent, right? Using graph neural networks, recurrent networks, and some multimodality with some embeddings of data. And I'm going to call all of that uses time series with the recurrent networks, graph data, and individual variables, multimodal learning. We call a modality a different type of data. So one modality is going to be a network, one modality is going to be the factors, and another modality is going to be the time series data. Right? So those three levels are going to build our multimodal network. When you hear about multimodal models in LLMs, they're called VLM, right? Lately are going to be, for example, images, audio, and text, right? So a multimodal model may be, for example, a GPT that receives instructions and gives you a video, or receives a video and describes it. That's also a type of multimodality. I apply those concepts in finance. Okay, first project. The first project is about corporate, right? I told you I was going to tell one corporate, one retail. This is the corporate project, right? So now these are all mid-caps. Why mid-caps? Because they are a lot more fun than the S&P 500. When you think about a company like Apple, Apple is larger, that's something like 70% of the world countries. So they are kind of subject to their own risk, right? A mid-cap is a company around $1 to $10 billion. They are subject to their internal economies. They are far more correlated. So the problem of correlated default becomes a lot more interesting. Right? So that's going to be our first problem. The idea here is that we have some sort of credit rating. We know there is a lot of overlap with this credit rating. So what we're going to do is we're going to group them into levels of risk, right? Like very attractive all the way down to very unattractive, right? When they are close to default. And what we have here is the level of investment, right? So if you are above this line, you are what's called investment grade, which means that you can be used in order to protect yourself from risk. Anything below that is the same as getting a stock, or is called an speculative bond, basically. So it's a company in which it's the same thing as if you were trading stocks. You're just running risk here. It's no sort of safe investment at all, right? So companies try really, really hard to stay here, because once you are here, you're going to get a lot of money from banks and institutions just that are going to use your bond to cover themselves for some sort of risk, and you're very happy. You're going to get a lot cheaper conditions. Just so you get an idea, a company at this level, a CAA1, may be paying 30–40% interest rate per year. A company AA, right? A AA, I'm not going to go a AAA, that basically pays nothing, like, or sometimes literally nothing. I mean, Germany has a 100-year zero coupon bond that pays 0.5% per year. What does that mean? Zero coupon means you pay at the end. So that thing literally will give you 0.5% per year composed 100 years from today. Right? So obviously people are not buying that. That's just to protect, to tie yourself to some sort of correlation to the German economy. Right? You're not expecting a payout from the German government 100 years from now, unless you're super optimistic about your life expectancy. Right? So this is where we're at. The other thing, as you can imagine, there are 15, 16 ratings here. They are super detailed, right? And they overlap a lot, especially in companies. So normally we group them because to create some sort of differences, right? So we're not going to predict 16, we're going to predict these 5 classes. Okay, so what I want is, of course, to build a multimodal temporal credit rating model using deep learning, right? So as I said, we're going to use the corporate financial statements. So, but not the wording of it. We're going to use directly structured data. So we're going to use structured regular data, and we're going to use the stock price to create something that we call an implied correlation, an implied connection, because we don't know if company A buys from company B. But what I do know is that when the volatility of one goes down, the volatility of the other also goes down. I see that not their stock prices, because stock prices can both have the same momentum because of the market. What I want to see if the volatilities are correlated. That is a lot more robust to understand if companies are connected, right? Their standard deviations are connected, as opposed to whether their stock prices are connected. How do I know that? Well, there is a very fun paper from 2021 from the Journal of Finance that shows it, right? I didn't do that. We know that from modern financial theory. So cool. Now I have that. So I'm going to connect companies implicitly depending on how their volatility move. After they are connected, I'm going to try to see whether I can use that in order to better predict a credit rating model compared to the state of the art. That's it, right? By using these models. Now, these words don't mean much better if I explain it this way. So how do we do it? So we have two families of models. Recurrent models are great at taking sequences of data, time series, and generating some sort of prediction. Graph models are great at taking graphs and generating some sort of prediction. But here what I have dynamic networks. That means I have snapshots of networks. Every day, for example, if you're looking at stock prices, the volatility may change. We actually don't use daily, it's too noisy, but we use something like monthly or something like that. But we have snapshots of how volatility correlates. I'll explain how I build that in a minute. And then that is going to generate a vector of the current financial standing of the company, right? And financial correlation of the company. And I'm going to have several snapshots. That's going to generate a time series. I'm going to feed a time series to the recurrent model that is expert in analyzing time series to generate a final prediction. So how does that look? I'm going to get different snapshots. I'm going to get the last n quarters. We use 6 quarters back, so we're looking at a year and a half back history, the financial statements, and the graph data corresponding to the last 90 days volatility matrices, right? So this one will enter a GNN. This one will enter directly a recurrent model. Each one of these will generate an embedding that then feeds this recurrent model. So the time series data is fed through here and generates one output. The graph data is fed through here that goes GNN first and then recurrent in order to make it temporal. So we have now one big encoding of all the data, graph data, and all its evolution. Graph data, its evolution. And I have one more embedding of all the time series data and its evolution. What do I do after I have that? I use a technique called data fusion, which is just a family to say I mash the data together somehow, right? What are the somehows? Normally you can use, one is literally mash them together. So you have two vectors, you paste them together and create like a bigger vector. That's called concatenation. But there are fancier methods, that something called cross attention, for example, in which you try to just plug the thing in a softmax in a logistic regression and try to weight it up and down depending on what happens. And after you get that, you get one output, which is a temporal graph, multimodal embedding, right? One vector with all the information. And that is fed to a decoder, which is just a fancier normal deep learning name of a whole bunch of layers, right, of dense layers that are going to generate a prediction. So these are highly parameterized, highly complex models, right, in the 500 million parameter order. That what they are doing is they are chewing up all of this data in this data architecture flow. And this is a simple model. There are far more complex, or there are some that you can fit this diagonally. We didn't want to go there basically because it worked and we just stopped there, right? We saw it work well enough, so we stopped there.
Sorry, quick question.
Sure.
So what's the embed 0, embed 1, embed n?
Yeah, time indexes.
No, one layer up from the GNNs, you have this embed 0, embed 1, embed n.
Yep.
What is that?
All right, these are the embeddings of the graph. In this case, this is nothing. So in fact,
what's the arrow from above?
So the graph data is a graph,
yes,
right? So it's like a matrix, an adjacency matrix. Yeah. Are we connected, 1 or 0? It enters the GNN, and the GNN is a model that will do something with the data, right? Normally what you will get is some sort of...
output of the GNN.
Exactly. Yeah, embed 0 normally is nothing. Yeah, no, that thing shouldn't be there. Yeah, yeah, sorry. So that one shouldn't be there, right? And then you pass it to an RNN, and you see how you are feeding then the first embedding to the second one, and so on and so forth, right? So in the simplest form, you remove these lines and you just feed it like that, down, down, and you use this H1 vector to compress all of the temporal information. That would be the simplest form, right? Yeah, cool. Okay, so the numerical data, so what we did was we did 10 years of data, 2010 to 2020, that's actually 11 years, 44 statements per company, 200 different financial features, right? So everything that we could get, we could have gone a lot more. We could have gone in speeches and stuff like that, but at first we wanted to measure just the correlated effect. And now we collect the daily stock prices for this. We convert this to price series of daily return. From that, we calculate the daily volatility series using the last 30 days, right? And then once you have the time series vector of the last 30 days volatilities, you calculate the correlation between these vectors for the multiple companies. Nothing too fancy there, right? And then that creates something like this, where you have, right, your autocorrelation is 1, you're correlated at 100% with yourself, and you have different levels of correlation that are going to be edge weights, right, depending on where how correlated you are with another company.
So these are weighted graphs?
Yes.
Okay, and what is the multimodal part?
The what?
The title you have the multimodal?
Yes, the numerical data. So you have numerical data, time series, modality 1, modality 2, your graphs. Remember, they don't have to be, I could have added, for example, modality 3, text. Your modalities need not be like vision and audio, can be any type of different data. In this case, you got graphs and time series data. Okay. There is a very interesting technique called triangularly filtered maximal graph that was invented from someone at Imperial College a couple of years ago, that uses tessellation, the same thing that you use for graph in video games, for cleaning graphs. Kamesh, my PhD student, actually thought about a way to use that in order to clean this type of graphs for our stuff for financial networks. And it works. So what you get is something like that. So this is the correlation network for 1 year. As you can see, it's perfectly clear. No one can understand a damn thing. That thing is a ball with nothing. So now what we want to do is we want to create the smallest graph that keeps the largest amount of information. You get that? How do you do that? Using triangles. So you try to find the most informative triangles that triangulates 3 companies, right? And then you place as little triangles as possible. That is what a video game does. So if you're trying to create a circle, you cannot create a circle with a set number of pixels, right? What you're going to create is a mesh, right, of triangles that when you look at them from far apart enough, they look like a circle or a sphere, right? The more triangles you have, the more of a circle it looks like. That's tessellation. This is the same theory, right? Or a very, very similar one. So this is like the tessellated network that keeps the maximum amount of information. Yep. So the weights is the correlation where you maximize the information content of the resulting graph as a whole. So this builds a matrix, right? So you want the matrix that looks the closest. Yeah? The most similar matrix that has removed a whole bunch of the noise of the correlation. You do get some small correlations because there may be some triangles that actually you need them to preserve the structure of the chain, right? Something like this. So maybe these 2 dots are not very well correlated, but if you disconnect them, the whole network falls apart. So in order to keep it together, you need to keep some correlations.
Is it known in theory that there exists a unique minimal graph or minimal graph?
That's actually a great question. What these guys prove that if you use triangles to connect them, then yes. But if you use anything else, no. right? In fact, one question that we got when we presented this, well, I didn't, Maria did, at KU was, why don't you use hexagons? I was like, yeah, you could, but no one has invented the hexagonally maximally filtered graph, right? Why stop there, right? I mean, why hexagons? Because they're the vestagons, right? So I don't know, but the thing is, we may actually use something different. Now we know this theory, so we just use it, right? We didn't really went too deep into this, but this gives you already something. What we are trying to do now, actually, and this is something that we are researching right now. I don't have an answer for you. I have no idea. I am trying to use an autoencoder deep learning to give me the best shape, basically, right? So to use the same information preservation thing to give me the minimum number of links, right? To see if we can do it data-driven. I don't have an answer for you yet, right? So that's what I'm trying. Stefan. Yes. Yes, that one is unique. The one that preserves the minimum information. You can create a whole bunch of this, right? But they are not going to have the property of maximum information. Yeah, it's because it uses triangle. It's not very hard to determine. It's like triangle inequality, right? So if you are using the triangle, the minimum triangle that captures information, you're going to find one that has the whole thing, right?
The hard part is understanding that you do this globally, right? Locally, I can imagine.
Yeah, but it's kind of the same idea. Yeah, it's kind of the same idea. Okay, cool. 44 graphs, 14,000 financial statements, 44 for each company. We divided, I mean, here you can, really this is something that you can see whether the paper is, has tried to not cheat or not, is that if they randomly select, if you see randomly select people in this and not doing time-based selection, they are obviously cheating because you're using correlations. If you mask one company, the whole point of the learning process is that it's going to identify the company. You need to do it in time. So we actually try to do it in two ways. Remember I told you that companies are entering and leaving the whole time? I'm going to use that. So the companies that are entering, I'm going to include them, right? I'm going to keep them apart in the test set. So they are new unseen companies. And the companies that are there in the data set already, I'll just keep them there, right? And I'm going to separate the report, but only I'm going to use the very final year. I'm going to use it as a test set, right? So it's something that this hasn't been seen by the data before, right? The whole network, the structure, the current thing hasn't been seen before. Right, sorry by the salad of numbers here. Let me walk you through here how you should read this. So we have seen companies, so companies that were already in the test set, and you have unseen companies, companies that haven't been on the train set, right? And here we have the performance of the baseline models, the ones that we compare ourselves to, transformers, LSTMs, DCNs, blah, blah, blah. And here you have the unseen results. And what you can see is that for example, for the seen companies, we get a pretty good model. An AUC of 0.94, so very good model, can predict the ratings pretty well, because remember, ratings are not very mobile. And we see a huge drop in unseen companies. So traditional models that are not temporal, these are static models, tend to be really, really, really good at capturing what they can see, basically, the companies that they see. Okay? Once we move to our proposals, we barely even win. In fact, we don't. We are within statistical margin of error for seen companies. So for companies that you already know, if you're just predicting companies that are not changing, don't waste your time. Just use a traditional model. Don't try to use something as fancy as the models that we have. But if you have a dynamic problem in which unseen companies appear, look at the jump. We jump almost 15% in training error. Sorry, in testing error. Why? Well, because our dynamic model is actually studying the dynamism of risk better, right? So you can see how that improves, is more structural than simply trying to replicate what you have already seen. So our models actually win on unseen companies, right? So this is a significant improvement when you have volatile markets. So the S&P 500 probably is not going to be that small because companies in the S&P 500 are super stable. The S&P 1000 though, that one has a 30% variation per year. So in 5 years, you're already seeing completely different companies, right? So maybe that is one that you want to keep an eye on. So takeaways, credit ratings show dynamic and multimodal features, so you can mix the two data. We see two signals, the signals in the financial statements and the corporate graphs. The paper has a lot more on exactly what that means and so on, but I don't have time for that, sadly. Our deep learning models are match or surpass the performance of Unimodal, and as I said, especially in unseen companies. And my biggest takeaway from this project is probably that for companies that are entering the stock market or are entering the index, you don't have that much information, and the current models actually are not very good, right? So models such as this one are probably a better alternative. So to finish today, in the last 15 minutes, I'm going to tell you about this very large project, but now in retail lending, right? This is still small businesses, but this is small businesses. You're talking about a dentist, a taxi driver, small businesses, anyone that operates as a small person. So same question. Can we improve now a credit score? These people use credit scores, right, for the company. So can we improve that? I'm going to use the same thing, multimodal network, but now I'm going to have a different thing. So same thing as I used before. So there we are. We have multiple networks across time, multiple snapshots, and I have data from the financial standing of the company, the time series of the financial standing of the company. Okay, same thing. I fuse my data, right? So it's the same architecture. Here, there is not much more gain. The only thing my students, I have Sandy now, did was he tried different types of architectures and different strategies. In the other one, we were kind of like, this is the architecture and that's it, just the proof of concept. Right here, let's go deeper into the different types of fusion. So maybe, remember that I showed how I first process the graph and then I process independently the numbers and I paste them together at the end. Maybe it works best if you fuse them at the very beginning, or maybe you need to do a two-stage fusion. So here we try different strategies, right? This is a paper that is coming out with the one where we define these strategies and their impact is a paper that's coming out with Rohitash Chandra from UNSW in Australia and our PhD student, Masa Tabakoli. The paper is coming out in ASOC in a few months. And of course, we use the same baselines as before. I'm sorry, I'm looking that way. I don't have the view here. So, and this is the decoder. Remember, I told you the decoder is just basically throwing a whole bunch of variables in it, right? And the binary cross entropy. The data set here is a lot more fun. So we were working with one of our partners, and these partners have this very interesting data set. They control 80% of the lending market for small businesses in that specific country, right? So we use 1.2 million loans, 218,000 companies, and a company could have more than one loan in the data set, right? And we have, after a big data set clean, so we got access to 215,000 variables over a huge data lake. Two of my PhD students worked for a year in order to clean this data, and they created two data sets. There are two papers coming on this. This is the one on application scoring for small businesses. There is another one on revolving lines coming. So we use July 2019 to December 2020 for training. Why? Because they had acquired a bank. They had bought a bank. So before that, their data was doing something completely different. And data from January 2021 to October 2021 for testing. And again, I divide by seen and unseen. I realized that that's super useful to identify performance. 6 months look back period in this case, so not quarterly data, this is monthly data.
I had a good idea what we have.
Oh yeah, David, can you mute yourself, please? Or if not, I can mute you. Thank you. And here we are, baseline models. We just throw this into a logistic regression and an XGBoost, and we got a 0.88 AUC. The Unimodal models win some. Once you put the networks in them, you win a bit more. So we start from 0.88. The data alone doesn't help much. The network data alone. This is just network data, nothing else. you still get to a very high result just with network data. So that's pretty cool. But when you mix the whole thing, here the models go consistently more complex. This is the one with everything. All the data, GIN, the whole thing, everything that we have. And we move from 0.87 to 0.915 in AUC, which is a significant gain, almost 5% gain, right? That for a portfolio of this large is several $100 million. So they were, let me put it this way, when we presented these results to them, right? One person said, I worked for a year over our retail lending to get a 1% increase. And you're saying that these barrels are giving you 5%? Yep, cool. So, yay. But we had something more. One difference of this project versus the one before, remember in the before we used these weird, fancy, correlated networks? Here has something far more simple, transaction and ownership. So we have transfers between companies, so we saw that there was like an explicit link. We knew that you had paid someone money. We could see that, right? And we also have an ownership network, which wasn't as good. So I'm going to focus in the transaction, okay? So keep in mind that we have transaction networks. And those ones can be directed because I transfer Seth or Seth transfers me. That creates a direction. But there is also a weight. If I pay Seth 70% of my expenses every month, you're a very significant provider for me, right? So we normalize this by the intensity of the trade, right? So that way we have a directed and a weighted network. And here is where we saw the greatest improvements. The first thing that we found out is that the directedness is not as important as the weightedness. So whether you are my supplier or my customer is not as important as how much I depend on you, either because of my sales or because of my purchases. That's the most important thing, right? But certainly both are more relevant. How are they more relevant? Well, this is the distribution of changing risk between upstream and downstream risk. Upstream risk means that you are my supplier. Downstream risk means that you are my customer. Upstream risk are bigger, so propagation is worse upstream than downstream. So that means if my supplier goes broke, my company is at a higher risk of being broke by exactly the Kullback-Leibler distance of these two, around 30% difference in risk. So significant drift. Think about it, makes sense. Normally a company that produces anything will have very few suppliers and hopefully a bunch of customers. So if one of those customers is going bust, then it's not as serious on average as if one of your suppliers goes bust and you need to find out a new supplier. The thing that we're doing here is that we are measuring quantitatively that impact, specifically across your own network, because we see it.
Wouldn't you want more suppliers then that supply the same thing as opposed to just?
But you normally don't. Think of a baker.
No, but in terms of robustifying that, if you're saying one supplier A defaults or doesn't supply me, then I'm dead in the water. But if I have two suppliers, A1 and A2.
Exactly. And that's the advice that we should give people. Yeah. but it's not usually the case. You usually buy from the cheapest supplier, right? And that's it, right? You don't normally diversify your supply chains, as we know from the pandemic, right? The one big issue is that we don't have diversified supply chains. Normally, the company is just going to go with the cheapest, right? Most companies. What you're saying is actually super true, is that given this risk, now think about it from the point of view of a bank. If your company is reporting that it has a robust network of suppliers, you can actually discount a few points on the rate, be more competitive with them, because you know that their upstream risk is lower. You can even throw it in here and see how that impacts, right? This actually gives you a quantitative measure. You get a probability outcome out of this, which is the big difference. We knew some of this at a macro level. We know that the upstream downstream effect at a macro level implies blah, 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 blah. There is a whole bunch of people studying robustness of supply chain networks at a country level. When here what we're doing is measuring the financial impact at an individual level. We know that you, with your network, have an impact of X from your factors, right? And just so you can see on the last slide, yep, fantastic. Yep, is this chap importance. How do you read this plot? I think that okay, so this one here is the most important variable. So basically, if you have some previous approval, is the most important thing. Basically, if I knew you from before, right, and I knew you were a good payer, is the most important thing. Okay, that doesn't really tell me everything. So here you see a lot of the variables that are important, right, and I can stop here for a bit more. Some of these are network variables, some of these are financial variables. But the most important plot is the one that's here. This is the change in variable importance for the variables that change the most between a pure model with no network information and a model with network information. So what information is encoded in the network variables that lose capability or gain capability to explain in relative terms, right? So let's start. So for example, if I knew you from before wasn't as important in a base model because the model tried to use a whole bunch of other variables to get some information. Once we put the network information directly, this one becomes the most important variable by far. Why? Because it's a unique signal that depends on your own robustness. You have shown to me that you're in a good standing. I know you, independent of what happens around you, right? So that is far more important if I'm considering what's around you, right? So it gains contribution. Some other, well, some whether that has some economic activity, but let me find another one. Okay, this one is interesting. This is the total generated revenue. The total generated revenue is super important for the XC boosting. It's not as important in our network model. Why? Because we're being much more careful in how we split the revenue across your supply chain. It is encoded in the graph, and it's now much more detailed because we look at who did you transfer to. And that's the beauty of it. The rest are all, you can tell the same story. Some of them are, for example, you don't really have much more to grasp. So for example, this is what was your total sales at the end of the year. It loses a lot of importance because you see more about the dynamism of the economy. You see the sales increasing, decreasing, so you're able to create a much more robust representation. So, conclusions. Networks are cool. They are useful. They allow you, especially in corporate companies and small businesses, you can see how risk propagates and moves in an interconnected system. One thing that we have about our modern economies is how interconnected they are, as we all knew quite well, right after the pandemic. Credit risk is super complex, and our base models using logistic regression, even using XC boosting, are not, because they are not considering. One thing is to make it complex using XC boosting, but the best way to improve your models is not by changing the methodology, it's by improving your data. And this is what we're doing here, right? And we're using a model that is able to leverage that data, of course. Right, and one thing, and I think that this is one of the biggest contribution of the work that we're doing, is that we are modeling contagion explicitly. We're not modeling like this fancy economic theory of contagion where you see that no, this is data, networks, your contagion risk is X, right? And that is the biggest thing versus traditional economic theory, right? What we're not doing is causal propagation, and that's what we are researching right now. There is a project that we submitted to CHERC, so maybe with some luck, I'm gonna be able to work on that starting next year. We have an agreement with the Bank of Canada. We're already thinking how to make it structural. So now, understanding if you're connected 4 companies downstream and the company here goes broke, that we see that that's the propagation of risk. That's now my research interest, how to make it causal and how to understand your individual contribution in a causal way, right? That doesn't exist now, so who knows where I'll be able to do it. I really like using SMEs for this because they are great for individual economic theory. And that's that. So thank you very much. Whole bunch of people collaborated on this, and we're very super duper thankful for it. And I'm happy to answer any questions you may have.